Imagine that you have lived your entire life in a room you believed was silent, and then, one day, someone hands you a device that lets you hear a single new frequency, and the room is suddenly full of voices. Not new voices, they were always there, you simply could not hear them. That is more or less what has happened to us as a species over the last few decades. Every time we build a new kind of telescope, tuned to a wavelength or an energy we could never reach before, the sky fills up with things we did not expect and cannot explain. Rings larger than galaxies, screams that last 1,000th of a second and outshine 1 billion suns, a dead star, 800 light-years away, that has been quietly raining antimatter on this planet since before we were human. And the strangest part is not any single signal. It is the pattern behind all of them. So make yourself comfortable and subscribe if you would like to keep drifting through the cosmos with me on nights like this one. Stay close, because by the end of this you may never think of the silence of space the same way again. Let us begin. Part 1. The Circle Nobody Could Name. In September of 2019, a radio astronomer named Anna Kopinska was sitting at her desk scrolling through images. They were not photographs, not the kind of pictures you would recognize. They were radio maps, visualizations of electromagnetic emissions at wavelengths invisible to the human eye, captured by one of the most powerful radio telescope arrays ever built. And as she scrolled, her eyes moving across map after map of the deep sky, she came across a shape that did not belong to anything she had ever been taught to recognize. The telescope feeding her those maps sits in the remote desert of Western Australia. It is called ASCAP, the Australian Square Kilometre Array Pathfinder, a network of 36 radio dishes, each one 12 metres across, all of them turned to the same patch of sky. It was designed to do something no radio telescope before it could do. It can survey enormous swaths of the heavens at once, and it is sensitive to faint, diffuse structures that older instruments had simply never been able to see. Its field of view is roughly 30 square degrees, which is the same area of sky covered by about 150 full moons, all at once. And it was feeding its data into a project with a simple, almost absurd ambition. The project was called EMU, the Evolutionary Map of the Universe, and its goal was to take the total number of known radio sources, roughly 2.5 million objects, the entire accumulated catalogue of every radio telescope in the history of the discipline, and increase it to about 70 million in a single survey. Picture that for a moment. Every radio telescope that has ever operated, across every observatory, across every decade since we first learned to listen to the sky in radio, had together found 2.5 million sources, and here was one instrument in one desert, preparing to find nearly 30 times that number on its own. When you build something that powerful, you're not just looking deeper, you're guaranteeing that you will see things nobody has ever seen. The only question is what they will turn out to be. And I want you to feel where this is happening, because the place matters. The dishes sit in a stretch of Western Australia so remote, so far from cities and highways and the electromagnetic chatter of modern life, that the silence there is part of the instrument. Radio telescopes are not like optical telescopes. They are not looking for faint points of light against the dark. They are listening for whispers of energy so weak that the spark of a passing car's engine or the signal from a mobile phone in a distant town can drown them out entirely. So the array was built in one of the quietest radio environments on the planet, a designated radio quiet zone, where the ordinary hum of human technology has been deliberately pushed away, so that the faint voices of the deep universe can be heard at all. Imagine standing among those 36 dishes at night. There are no street lights. The Milky Way arches overhead so brightly it casts a shadow. And all around you, in perfect silence, these great white surfaces are tilted toward the same patch of sky, drinking in wavelengths your eyes will never register, turning the invisible into numbers. It is one of the most patient acts in all of science. You point the dishes, and you wait, and you let the universe pour itself into your machine, and only later, sometimes years later, do you find out what it was trying to tell you. Now, here is the part that surprises people. Kapinska was not searching with an algorithm. She was not running the data through some vast artificial intelligence trained to flag the unusual. She was browsing the early images with her eyes. Old-fashioned human pattern recognition, the same tool that has driven nearly every major observational discovery in the history of astronomy. And as she scrolled, she noticed something that did not fit. A shape in the data that she could not match to any known type of astronomical object. It was circular. It was faint. It was enormous. A ghostly ring of radio emission hanging in deep space, like a cosmic smoke ring, billions of light years from Earth, with no visible counterpart at any other wavelength. There was no optical light there, no infrared, no X-ray, nothing. Just radio waves, forming a near-perfect circle in the void. Imagine sorting through a stack of ordinary photographs and finding, halfway down, a picture of something that should not be able to exist, and having no name for it, no category, no explanation. That is roughly where she stood. So she did what an honest scientist does when the universe hands them something genuinely new. She labelled the image with 2 letters and a question mark. She wrote, WTF. And I want you to hold on to that little moment, because we are going to come back to it, much later, and it is going to mean something quite different by the time we do. A few days later, her colleague, a radio astronomer named Emil Lentz, found a second one. Then the team found a third, then a fourth. That fourth one turned out to be hiding in archival data from the giant meter-wave radio telescope in India, captured all the way back in 2013, but never noticed by anyone at the time. The object had been sitting in a data file for 6 years, fully formed, fully real, waiting for someone to recognize it. And when they finally did, it was confirmed by multiple telescopes, at multiple frequencies, and nobody, not one person on the planet, had any idea what it actually was. Here is the strange thing. A scientist had seen this coming. Ray Norris, a professor at Western Sydney University and the leader of the EMU project, had predicted years earlier that this new generation of radio telescopes would discover things that could not be explained by existing theories. He was so confident of it that he had coined a term for these anticipated surprises in advance. He called them WTFs. He expected the universe to hand him things he could not explain. He just did not expect one to arrive so quickly, and he certainly did not expect it to look like this. Because when the team measured it, the scale was almost impossible to take seriously. A perfect circle of radio emission, roughly 1 million light-years across. To give that a shape you can feel, our entire galaxy, the Milky Way, with its 200 billion stars, is about 100,000 light-years wide. This ring was 20 times wider than that. It was visible only in radio wavelengths, with no known mechanism in all of physics capable of producing it. So Norris and his team gave these objects a name, and the name was deliberately, almost stubbornly understated. They called them odd radio circles, ORCs, as if the strangest structures anyone had found in years were merely a little bit odd. As of late 2025, 8 of these odd radio circles have been confirmed, with several more candidates still under investigation. And the reason I am starting here with a woman at a desk and 2 letters and a question mark is that this is not really a story about one ghostly ring in the sky. This is a story about a pattern that, once you see it, you cannot unsee. Because the odd radio circles are not an isolated curiosity. They are the first thread in something much larger and much stranger, and the universe has been holding the other end of it for a very long time, waiting for us to notice we were even holding on. There is something worth pausing on in the way this discovery actually happened, because it sets the tone for everything that follows. We tend to imagine that, in the age of supercomputers and artificial intelligence, the great discoveries are made by machines. We picture algorithms combing through oceans of data, flagging the anomalies, surfacing the patterns no human could ever spot. And to be fair, machines do a great deal of that work now, and they do it well. But the odd radio circles were not found by a machine. They were found by a person, looking. A trained human eye, moving across image after image, carrying with it a lifetime of knowledge about what the sky's supposed to look like, and noticing, in a single instant, that this particular thing did not belong. The whole discovery rested on the oldest tool in the trade, the one no instrument has ever fully replaced. Curiosity, attached to a pair of eyes, attached to a mind that knew enough to be surprised. And you will see that exact same tool surface again and again in this story, at the centre of nearly every signal we're about to follow. Keep an eye out for it, so let us follow that thread and see where it pulls. Part 2, 8 ghosts and 3 suspects. Let us stay with these circles a little longer, because before you can understand why they unsettle astronomers, you have to understand what they are made of and what they are not. Each odd radio circle is a ring of synchrotron radiation. That is a specific kind of electromagnetic emission, and it is produced under very particular conditions. You get synchrotron radiation when electrons spiral through magnetic fields at velocities approaching the speed of light. As those electrons whip around the field lines nearly as fast as light itself, they shed energy in the form of radio waves. So when you see a structure glowing in synchrotron emission, you're not looking at something warm or something burning. You're looking at the signature of magnetic fields and particles moving at relativistic speed. You're looking at violence, frozen into a shape, and the shape itself carries a clue. The rings are edge-brightened. That means the outer boundary of each circle glows more intensely than the interior, the way the rim of a soap bubble catches the light more strongly than its centre when it is lit from within. Edge brightening is what you expect from a hollow shell, a three-dimensional bubble of emission that we are seeing in projection. When you look at a bubble, you are looking through more of its glowing skin at the edges than you are through the middle, so the edges look brighter. These circles behave like bubbles, spheres of radio light, seen flattened against the dark. Now, the scale. I told you a single odd radio circle could be 1,000,000 light-years across, but the confirmed examples range in estimated diameter from several 100,000 light-years to over 2,000,000 light-years. 2,000,000 light-years. Let me put that number where you can feel its weight. Our entire galaxy, the Milky Way, all 200 billion of its stars, all of its spiral arms, its core, its halo, every star you have ever seen with your naked eye and trillions more you have not, fits inside a sphere roughly 100,000 light-years wide. You could line up 20 Milky Ways, edge to edge, and they would still fit across a single one of these rings. These are among the largest individual structures ever detected anywhere in the universe. And on first encounter, they appear to have absolutely no business existing. It helps to try to walk that distance in your mind, even though no mind can really do it. Light. The fastest thing there is, the thing that crosses from the sun to the earth in 8 minutes and circles our entire planet 7 times in a single second, would take 2,000,000 years to cross from one edge of the largest odd radio circle to the other. 2,000,000 years. When light set out across one of these rings, our ancestors were not yet what we would call human. By the time that beam of light reached the far side, entire species had risen and gone extinct on Earth. Ice ages had come and retreated, the whole drama of human prehistory had played out. And that is just the time to cross one of these objects once. Now consider that the ring itself is not solid. It is not a wall. It is a delicate shell of plasma, a structure so thin and so faint that it gave off no light at all, that we could detect for the entire history of astronomy, right up until 2019. We are talking about something larger than a galaxy, more diffuse than a wisp of smoke, glowing only in radio, hanging in the dark between the galaxies like a soap bubble the size of a small universe. The mind reaches for it and slips off. That slipping, that failure of intuition, is itself part of the data. When a structure is so large that your imagination cannot hold it, you're usually looking at something the textbooks did not fully anticipate. So the team did what good scientists always do first. Before asking what something is, they worked out everything it is not. and one by one, the obvious explanations fell away. They are not supernova remnants. When a star explodes, it leaves behind an expanding shell of debris that glows in radio, and those shells can look circular. But supernova remnants are typically a few dozen light-years across, and they sit near the galactic plane, embedded in the disk of their host galaxy, close to where stars live and die. The odd radio circles are hundreds of thousands of light-years wide, and they hang far from any galactic plane, out in the open dark. The scale is wrong by a factor of around 10,000. It would be like mistaking a continent for a coin. They are not planetary nebulae, the delicate glowing shells thrown off by dying sun like stars. Those are tiny by comparison, and they live inside galaxies, not dwarfing them. They are not the radio lobes of active galactic nuclei. When a supermassive black hole at the heart of a galaxy launches jets of plasma out into space, those jets inflate enormous lobes of radio emission. But those structures are elongated and lopsided, stretched out along the direction of the jet, asymmetric by nature. The odd radio circles are almost perfectly round. Symmetry is exactly what jets do not give you, and they are not Einstein rings. That is the beautiful effect where the gravity of a massive foreground object bends the light of a more distant source behind it, smearing it into a ring. It is real, and it does make circles. But an Einstein ring requires that massive foreground lens sitting right in the middle doing the bending, and when astronomers looked at the centres of the odd radio circles, they did not find a lens. What they found instead was something nobody had ordered. At the centre of some of these rings, sitting precisely at the geometric heart of a structure 2 million light-years wide, there was a galaxy. Specifically, a massive elliptical galaxy. 3 of the confirmed odd radio circles, the ones catalogued as ORC1, ORC4, and ORC5, each have an elliptical galaxy parked exactly at their centre. And the probability that this is a coincidence, that a galaxy just happened to land at the dead centre of a ring spanning 2 million light-years by pure chance, is vanishingly small. The galaxies are not bystanders, they are connected to the circles. They are almost certainly responsible for creating them, but that only sharpens the question. How does a single galaxy carve a ring of radio light larger than itself by a factor of 10 or more? 3 hypotheses are on the table. None has been confirmed, none has been ruled out. The first is a merger of supermassive black holes. When 2 galaxies collide, and over hundreds of millions of years their central black holes spiral inward and finally merge, the event releases an extraordinary burst of gravitational and electromagnetic energy. That energy could propagate outward as a spherical shock wave, sweeping through the thin gas between galaxies, accelerating electrons in its path and producing a bubble of synchrotron radiation. Seen from our vantage point, billions of light-years away, that expanding bubble would appear as a ring, a circle that is really the echo of 2 black holes becoming one. The second hypothesis is a starburst termination shock. In this picture, the central galaxy went through a brief, furious period of star formation, producing millions of new stars in just a few tens of millions of years. The combined stellar winds from all those young stars, amplified by the supernova explosions that followed as the most massive of them died, pushed a shock wave outward through the surrounding medium. Over billions of years, that shock kept expanding until it reached the enormous scale we now observe, exciting electrons along its leading edge and lighting up the characteristic ring. In this version, the circle is the long, slow exhale of a galaxy that once built stars at a frantic pace. The third hypothesis is simpler, but harder to confirm. The odd radio circles might be the end-on view of radio jets from an active galactic nucleus. Remember those lopsided, elongated lobes I said the circles were not? Well, what if we are simply catching one of them from an unusual angle? If we happen to be looking straight down the barrel of a jet, the 2 lobes of radio emission on either side of the galaxy could overlap, one behind the other, and project onto our sky as a ring rather than the elongated double structure we normally see. The alignment would have to be almost exact. But the universe is vast and improbable alignments do happen somewhere, eventually. So, which is it? The honest answer is that the data does not yet tell us. It does not favour one explanation over the others. And I want to dwell on that for a second because there is a temptation, when you hear three competing explanations, to assume that one of them must be right and the scientists just have not figured out which yet. Sometimes that is true, but sometimes, in the history of this field, the real answer turned out to be a fourth thing that nobody had put on the list, a possibility that no one had thought to consider, because the phenomenon itself was so new that the imagination had not yet caught up to it. When pulsars were first discovered, the very first serious hypothesis on the table was that the regular pulses might be a signal from an extraterrestrial civilization. The discoverers half-jokingly labelled the source LGM-1 for little green men before they worked out it was a spinning neutron star. The lesson is not that aliens are the answer. The lesson is that when something genuinely new arrives, the first explanations we reach for are drawn from the catalogue of things we already know, and the truth may lie outside that catalogue entirely. The odd radio circles may end up being a black hole merger, or a starburst shock, or an end-on jet. Or they may end up being something we have not yet learned to imagine. What the data does tell us, unambiguously, is that something happened in those central galaxies. Something violent enough to sculpt a structure of radio-emitting plasma larger than anything we had ever previously encountered. Something that occurred billions of years ago, and whose faint ringing echo we're only now able to detect, because our instruments have only just become sensitive enough to catch it. And that last part is the part to hold on to. The circles did not appear in 2019. They have been hanging there, glowing quietly in radio for a very long time. 2019 is simply the year we grew the right eyes. Keep that thought close, because the next signal in this story makes the same point, and it makes it about something far closer to home than a galaxy at the edge of the visible universe. Part 3. It is not there. 800 light-years from Earth, there is something else. Something older. Something far closer than a ring of radio light at the rim of the cosmos. And it has been pouring energy out across space for longer than our entire species has existed. And until quite recently, we had no idea it was there at all. The story begins in 1972 with a small satellite that detected something it was never designed to find. The satellite was NASA's second small astronomy satellite, known simply as SAS-2, and it was scanning the sky for sources of gamma radiation. Gamma rays are the highest energy form of light in the entire electromagnetic spectrum. They are produced only by the most violent processes the universe has to offer. Supernova explosions, matter spiralling into black holes, collisions between particles accelerated to nearly the speed of light. Gamma rays are the fingerprints of cosmic violence, and SAS-2 was built to map where they came from. And in its data, the satellite recorded an intense source of gamma rays streaming out of the direction of the constellation Gemini. The source was bright. It was persistent, holding steady over time rather than flaring and fading. And it had no counterpart at any other wavelength. No optical light, no radio waves, no infrared, nothing. The satellite could see the gamma rays perfectly clearly, but the source itself appeared to be completely invisible. It was radiating energy at the most extreme end of the electromagnetic spectrum, and doing nothing else, as if something enormously powerful was hiding in plain sight, broadcasting its presence in one single frequency, while remaining utterly silent in every other. There was a practical problem too. The angular resolution of SAS-2 was poor, roughly 2.5 degrees at the energies it observed. What that means, in plain terms, is that the satellite could tell you the source existed somewhere inside a fairly large patch of sky, but it could not tell you where inside that patch. To give you a sense of how frustrating that is, 2.5 degrees is about 5 times the width of the full moon as it appears in our sky. So imagine someone tells you there is a single specific house, somewhere, that is on fire and broadcasting a distress call. But the best they can do is point to a region 5 full moons across and say, it is somewhere in there. And that region is not empty. A patch of sky 2.5 degrees wide contains thousands of stars and many other known objects, any one of which might, in principle, be the culprit. Identifying which specific object was producing the gamma rays out of all those thousands of candidates was simply impossible with the technology of the day. The gamma rays were loud and clear, the address was hopelessly vague, and gamma rays are notoriously difficult to focus. You cannot build a gamma-ray telescope the way you build an optical one, with a lens or a mirror that bends the light to a sharp point, because gamma rays punch straight through ordinary mirrors. So the very nature of the radiation conspired to keep the source hidden. So the source was filed away, catalogued, and given a name by an Italian physicist named Giovanni Bignami, a man who would go on to spend the next 2 decades of his career trying to find it. He called it Geminga. On the surface, the name was just a contraction, Gemini Gamma Ray Source, squeezed down into a single word. But Bignami had a sense of humour, and in his native Milanese dialect the word Geminga means something else entirely. It means, it is not there. He looked at this powerful, persistent, utterly invisible source, and he named it, in his mother tongue, the thing that is not there. Remember that. We will need it. For 20 years, Geminga remained one of the most maddening objects in all of astrophysics. Consider the contradiction at the heart of it. This was the second brightest persistent source of gamma rays in the entire sky. The only thing that outshone it was the Vela pulsar. Around 99% of its total energy output came out in the gamma ray band. It was pouring radiation into space with an intensity that flatly demanded an explanation. And yet, every single attempt to identify it at any other wavelength failed. Radio telescopes pointed at it and found nothing. Optical telescopes pointed at it and found nothing. The source was there, screaming in gamma rays, and not there, silent in everything else, at the same time. It was a paradox that Bignami's little pun captured perfectly. The whole community knew that something extraordinary was hiding in the constellation Gemini. They simply could not find it. It is hard, from the comfort of the present, to appreciate how much patience that required. 20 years is not a footnote in a career. It is most of a working life. Giovanni Bignami was a young man when he first catalogued Geminga, and he would be approaching the end of his most productive decades by the time the answer finally came. Think about what it means to chase a single invisible object for that long. Grant proposals written and rejected, telescope time requested and denied, or granted and wasted on yet another null result. Colleagues quietly suggesting that maybe it was time to move on to something more tractable, something that would actually yield a paper. And through all of it, the conviction that the thing was real, that it was up there, that it was important, and that the only obstacle between the question and the answer was that the right instrument had not yet been built. There is a particular kind of faith in that. Not faith in the supernatural, but faith in the universe's eventual willingness to be understood, if only you are stubborn enough, and if only the technology catches up in time. Geminga rewarded that faith, but it made everyone wait. And the lesson buried in that long wait is the same lesson the odd radio circles taught us, just told more slowly. The signal was there the whole time. The limitation was never in the source, it was in the instrument and in our patience. The first crack in the wall came in 1983. Bignami and his team used the Einstein X-ray satellite to detect a faint X-ray signal coming from the general direction of Geminga. The signal was weak, far too weak to pinpoint the source precisely, but it did something important. It narrowed the search area. It took that wide, hopeless patch of sky and shrank it. And then came another long wait. 8 more years of technological development, of new instruments being designed and built and launched, of satellites being aimed, again and again, at the same stubborn corner of the constellation Gemini. And finally, in March of 1991, the answer arrived. It arrived from 2 separate missions, almost simultaneously, which is exactly the kind of confirmation scientists dream of. The German-built Rosat satellite, an X-ray observatory sensitive enough to resolve individual sources within crowded fields, detected a signal from Geminga's location that did something the source had never been seen to do before. It pulsed. It repeated with a period of 0.237 seconds, flashing on and off roughly 4.2 times every second, with the steady, relentless precision of an atomic clock. And within weeks, that exact same periodicity was confirmed in gamma rays by the Egret telescope aboard NASA's Compton Gamma Ray Observatory. The X-rays and the gamma rays were pulsing in perfect synchrony. That settled it. The thing that was not there was not a cloud. It was not a nebula. It was not some distant galaxy. It was a pulsar, a neutron star. The collapsed remnant of a star several times more massive than our Sun, a star that had exploded as a supernova roughly 300,000 years ago, and left behind a core so dense that all of its mass had been crushed into a sphere only about 20 kilometers across. And that core was now spinning on its axis more than 4 times every second, sweeping beams of radiation across the cosmos like a lighthouse built from the corpse of a dead star. After 20 years, the ghost in Gemini finally had a body. But as the next part will show, identifying what Geminga was only revealed how deeply strange it truly is. Because this was no ordinary pulsar. Part 4, the pulse that resolved. I want to slow down here and put you in the room, because the moment Geminga resolved is one of the quietly great moments in modern astronomy, and it deserves more than a date. It is March of 1991. The data is coming in from Rosat, the X-ray observatory, and from Egret aboard the Compton Gamma Ray Observatory. For 19 years, this source has been a smear, a bright stain of gamma rays with no face, no fixed location, no identity. Generations of instruments have failed to pin it down, and now, on a screen, a signal that had always looked like a steady glow begins to reveal a hidden rhythm inside itself. The light is not constant, it is flashing, on, off, 4.2 times a second, every second, never varying, never drifting, holding its beat with a precision that no natural process other than a spinning neutron star could possibly produce. Somewhere 800 light-years away, the burned-out heart of a long-dead star is turning and turning and turning, and with each rotation it sweeps a beam past the Earth, and we are finally, after 20 years, fast enough and sensitive enough to count the flashes. And here is the line that lands if you have been paying attention. Bignami named it, in his own dialect, the thing that is not there. And in that moment in 1991, the joke quietly inverted itself. Because it was always there. It had been there for 300,000 years, spinning 4 times a second, flooding our sky with gamma rays the entire time. It was never absent. We were simply blind to it. The name was never really a statement about the universe. It was a confession about us. But Geminga was not an ordinary pulsar, and the ways in which it was abnormal would take years more to fully appreciate. The first abnormality was the strangest, because it cut against the very definition of what a pulsar was supposed to be. At the time Geminga was identified, every single known pulsar in existence had been discovered through its radio emissions. Pulsars were, by definition, radio objects. They were found by radio telescopes, catalogued by radio astronomers, and understood entirely through the framework of radio pulse analysis. If you had asked an astronomer in 1990 what a pulsar was, the answer would have included the word radio somewhere near the beginning. And Geminga broke that definition in half. It was the first pulsar ever identified that produced no detectable radio pulses at all. It screamed in gamma rays, it whispered in X-rays. And in radio, the band where every one of its siblings had been found, it was effectively mute. The radio lighthouse beam, if it existed at all, was either pointed away from Earth, or it was so weak at the frequencies anyone bothered to observe that decades of searching had turned up nothing. The explanation for that radio silence did not arrive until 1997, and when it came, it taught a lesson that this entire story keeps repeating. 3 independent observations from the Pushchino Radio Astronomy Observatory in Russia, finally detected extremely faint radio pulses from Geminga. They were real. The pulsar was not radio silent after all. But the pulses were at a frequency of around 100 megahertz, which is far below the range where most radio telescopes had been searching. Standard pulsar surveys focused their attention on frequencies between 430 and 1600 megahertz, because that is where pulsars were expected to be loudest. Geminga was broadcasting below the band that anyone had thought to listen to. It was not silent. It had been sending out its signal for 300,000 years. We were simply not tuned to the right frequency. We were, quite literally, not listening correctly. Hold on to that sentence too, because it is going to grow, by the end of this, into something much larger than one pulsar. The second abnormality was Geminga's motion. Using observations from the European Southern Observatory's telescopes in Chile and from the Canada-France-Hawaii telescope, Bignummy's team discovered that Geminga was moving across the sky at an extraordinary rate, roughly 0.2 arcseconds every year. For a neutron star 800 light-years away, that tiny angular shift translates to a velocity of about 210 kilometers per second. Let me make that real. This is the corpse of a dead star containing about 1.5 times the mass of our entire Sun, compressed into a sphere roughly 20 kilometers in diameter, and it is hurtling through the galaxy at around 756,000 kilometers per hour. At that speed, Geminga will cross a distance equal to the apparent width of the full moon on our sky in just over 10,000 years. In astronomical terms, that is sprinting. And the reason it moves so fast tells you something about how it was born. When a massive star reaches the end of its life and collapses, the explosion that follows, the supernova, is almost never perfectly symmetric. One side blows out a little harder than the other, and just as a balloon shoots across a room when you let the air out of one side, the asymmetry of the explosion gives the collapsed core a tremendous kick. The neutron star is launched out of the wreckage of its own death like a cannonball, and it carries that velocity with it for the rest of its existence, coasting through the galaxy, because there is almost nothing in the near vacuum of interstellar space to slow it down. So when we see Geminga sprinting, we are watching the recoil of an explosion that happened 300,000 years ago, still playing out, still carrying this dead star away from the place where it was made. To picture a sphere only 20 kilometers across, smaller than many cities, but heavier than the entire Sun, moving at 756,000 kilometers per hour, is to picture something that violates every intuition we have about how mass and size and speed are supposed to relate to one another. It is denser than an atomic nucleus, smaller than a county, more massive than a star, and faster than anything you will ever see move. Everything about it is extreme, and it has been quietly extreme, 800 light-years away, for the whole of human history. And the third abnormality was the most beautiful, and it was not revealed until 2003, when a team led by the astrophysicist Patricia Caraveo used the European Space Agency's XMM Newton X-ray Observatory to look closely at Geminga as it raced along. They discovered two ghostly tails of X-ray emissions streaming out behind it. The tails stretch roughly 3 trillion kilometers across the sky, trailing behind the pulsar like the wake of a ship cutting through dark water. They are created by the interaction between Geminga's intense magnetic field, its rapid rotation, and the thin interstellar medium it is ploughing through. As the pulsar drives forward at 210 kilometers per second, it compresses the gas and magnetic fields directly ahead of it by a factor of 4, creating a bow shock, a crescent-shaped wave of compressed material in front of it, exactly like the wave that builds at the prow of a fast boat. Behind that shock, electrons and their antimatter counterparts, particles called positrons, are accelerated to extreme energies by the pulsar's spinning magnetic field, and they spiral outward along the enhanced field lines, emitting X-rays as they go. The result is a pair of luminous tails, visible only in X-ray light, marking the path of a dead star's passage through the galaxy, like the contrails behind a jet aircraft. So now we have the full strange portrait, a 20-kilometer corpse, 800 light-years away, 300,000 years old, spinning 4 times a second, mute in radio for the wrong reasons, sprinting through the galaxy, dragging glowing trails behind it. It is one of the most peculiar objects within 1,000 light-years of Earth. And yet, the single most consequential thing about Jaminga is none of these. It is not the spin, or the silence, or the speed, or the tails. It is what Jaminga has been quietly doing to us, to the Earth, to every living thing on this planet, for longer than human beings have walked upright. And that discovery did not come until 2017. Part 5. The Antimatter over our heads. To understand what Jaminga has been doing to us, we have to go up, 200 miles above the surface of the Earth, to the outside of the International Space Station, and to a machine that was switched on in 2011. The machine is called the Alpha Magnetic Spectrometer, and it is a state-of-the-art particle detector, bolted to the exterior of the space station, sweeping up the particles that rain down on our region of space from across the galaxy. Among the things it was built to detect were positrons. A positron is the antimatter counterpart of an electron. It has the same mass but the opposite electric charge, and when a positron meets an electron, the two annihilate each other in a flash of energy. Antimatter sounds exotic, like something out of science fiction, but it is produced naturally by a number of cosmic processes, including radioactive decay and the collisions of cosmic rays with interstellar gas. Physicists fully expected to find some positrons in the flux of particles bombarding the Earth. That was not surprising. What was surprising was the quantity. The Alpha Magnetic Spectrometer detected far more high-energy positrons than any existing model could explain. By 2013, the detector had recorded over 400,000 positrons, the largest sample of cosmic ray positron data ever collected. It increased the world's total stockpile of cosmic ray positron data by a factor of 100, and the numbers it returned simply did not fit. There was an excess, a surplus of antimatter particles arriving at Earth, and nobody could account for where they were coming from. Something out there was manufacturing antimatter and flinging it toward our planet in quantities that defied prediction. For a few years, this became one of the most exciting unsolved problems in physics, because of what the excess might have meant. Some physicists hoped that these surplus positrons were a signature of dark matter annihilation. Dark matter is the invisible substance that makes up most of the matter in the universe, and we have never directly detected a single particle of it. But there is a theoretical process by which particles of dark matter, colliding with each other, could annihilate and produce pairs of electrons and positrons. If that were the source of the excess, it would have been one of the most important discoveries in the entire history of science. It would have been the first direct detection of dark matter, caught in the act through the debris of its own self-destruction. The excitement was enormous. The stakes could hardly have been higher. For a few years, this was one of the most tantalizing leads in all of physics, because dark matter is the great open scandal of modern science. We know it is there. We can see its gravity holding galaxies together, bending light, shaping the largest structures in the cosmos. By every measure, it outweighs all the ordinary matter in the universe by a factor of 5 or more. And yet, despite decades of searching, despite enormous detectors buried deep underground in old mines, to shield them from interference, we have never caught a single particle of it directly. So when the positrons started pouring in, more than anyone could explain, the hope was electric. Maybe this was it. Maybe the dark matter, invisible everywhere else, was finally showing its hand, announcing itself through the debris of its own annihilation, raining the evidence down on a detector strapped to a space station. And the answer, when it finally arrived, pointed not toward dark matter, but back toward the ghost that was not there. In 2017, the High-Altitude Water Cherenkov Gamma Ray Observatory, known as HAWC, located high on a mountainside near Puebla, Mexico, detected a small halo of gamma radiation surrounding Jaminga. These were not low-energy gamma rays. They carried energies between 5 and 40 trillion electron volts, which is trillions of times more energetic than visible light. The halo was being produced by positrons and electrons, accelerated by the pulsar, colliding with the ambient starlight around it, and boosting that light up to gamma-ray energies through a process called inverse Compton scattering. In plain language, Shaminga was surrounded by a cloud of high-energy particles, and those particles were lighting up the space around the pulsar in gamma rays. Then, in 2019, a team led by the astrophysicist Mattia Di Mauro used a full decade of data from NASA's Fermi Gamma Ray Space Telescope to reveal the true extent of that halo. And it was not small, it was vast. At an energy of 10 billion electron volts, the halo spanned 20 degrees of the sky, which is roughly the area covered by the entire Big Dipper. At lower energies, it was even larger. If human eyes could see gamma rays, Jaminga's halo would dominate the night sky, covering an area around 40 times larger than the full moon. There is an invisible cloud of the most energetic light in the universe, surrounding a dead star 800 light-years away, and it has been hanging over our heads for longer than civilization has existed. And here is where it all comes together. Di Mauro's team determined that Jaminga alone could be responsible for as much as 20% of the excess high-energy positrons detected by the alpha magnetic spectrometer up on the space station, 20% of a galaxy-wide mystery traced to a single dead star. And once you extrapolate from that one pulsar to the cumulative contribution of all the pulsars scattered across the Milky Way, the conclusion becomes clear. The researchers concluded that pulsars are the most likely explanation for the entire positron excess. The antimatter mystery that had consumed a decade of research, that had tantalized physicists with the dream of detecting dark matter, was most likely being caused by the spinning corpses of dead stars sprinkled across the galaxy, accelerating particles to relativistic speeds and flinging them out into space in invisible streams of antimatter that wash over every planet, every moon, every asteroid in their path. Now sit with the full weight of this. Jaminga is 800 light-years from Earth. It has been radiating gamma rays and manufacturing antimatter for roughly 300,000 years. Its halo, if you could see it, would be one of the largest structures in our entire night sky. And until 1972, we did not even know it existed. Until 1991, we did not know what it was. And until 2019, we did not understand how far its influence reached. A single pulsar, 20 kilometers across, has been showering our planet with antimatter for thousands upon thousands of years, through our atmosphere, through the ground, through your body as you sit here. And the only reason we know any of it is that we built a particle detector and bolted it to the outside of a space station, and we got lucky enough to look. Let me try to make the timescale personal, because 300,000 years is another one of those numbers that slides off the mind. 300,000 years ago, anatomically modern humans were just beginning to appear on the African continent. There were no cities, no writing, no agriculture, no wheel. Our ancestors were small bands of hunter-gatherers, napping stone tools, watching the same stars we watch now wheel overhead. And during that entire span, every single night the gamma rays from Jaminga were arriving at the top of Earth's atmosphere, and the antimatter it manufactures was washing through the solar system. Every generation of humans who ever lived, every one of the roughly 10,000 generations that separate us from those first modern people, lived their whole lives bathed in the invisible output of this dead star, and not one of them knew. The Egyptians who built the pyramids did not know. The astronomers of ancient Babylon, who track the planets with extraordinary care, did not know. Galileo, who first turned a telescope to the sky, did not know. Newton did not know. Einstein, who rewrote our understanding of gravity and light, lived and died without knowing that Jaminga was there, raining antimatter on the world. The first human being to learn of its existence was born in the 20th century. And the reason is not that Jaminga was hiding. It is that we did not have the eyes. The antimatter was always arriving. We were simply not equipped to notice. So I have to ask the question that this naturally raises. What else is out there, right now, doing something to us, that we have simply not yet built the instrument to detect? because the next signal in this story is going to push that question further than you might be comfortable with. Part 6. The Burst in the Basement. In 2001, the Parkes Radio Telescope in New South Wales, Australia, recorded a pulse, and nobody noticed. The telescope was surveying the region of sky near the Small Magellanic Cloud, one of the small satellite galaxies that orbits our Milky Way, and it was looking for pulsars. The data it collected was archived, stored on servers, filed away, and, for all practical purposes, forgotten. 480 hours of recorded sky, set aside like old newspapers stacked in the basement of a library, the kind of thing nobody expects to ever open again. And inside that archive, buried in the numbers, the pulse sat untouched for 6 years. In 2007, a professor at West Virginia University named Duncan Lorimer assigned an undergraduate student named David Narkovich to go back through that archived data and search it. Not for pulses this time, but for something else. For bright, isolated, one-off pulses that might have been missed by the standard search algorithms, because those algorithms had been designed to find repeating signals, regular flashes that come around again and again, not single, sudden, never repeated events. Narkovich was looking for a needle in a haystack the size of a small country, and against the odds, he found one. It was a single burst of radio emission, less than 5 milliseconds long, so bright that it had saturated the detector when it hit, in the primary beam of the telescope, 30 Janskys of peak flux. To give that a sense of scale, most astronomical radio sources register in the millijansky range, thousandths of a single Jansky. This signal was tens of thousands of times brighter than typical background sources. It flared, it peaked, and it vanished, all in less time than it takes a hummingbird to beat its wings a single time. There and then gone. And the burst had a distinctive signature, a fingerprint that told the astronomers something crucial about where it had come from. Its higher frequency components arrived at the telescope slightly before its lower frequency components. That effect is called dispersion, and the cause of it is one of the most useful quirks in radio astronomy. When radio waves travel through ionized gas, through space filled with free electrons, those free electrons slow the lower frequencies down more than the higher ones. The effect is cumulative. The more gas the signal passes through on its journey, the greater the delay between the high and low frequency parts of the pulse by the time it arrives. So if you measure the amount of dispersion in a burst, you can estimate how much ionized material the signal travelled through to reach you. It is like reading how far a sound has travelled by how muffled it has become. And the dispersion of this burst was enormous, far too large to be explained by the gas within our own galaxy. The signal had clearly travelled through the intergalactic medium, through the vast tracts of thin gas that lie between galaxies. It had come from outside the Milky Way. When Lorimer's team ran the numbers and calculated the distance, they arrived at a figure of roughly 1.5 to 3 billion light-years. Let that distance settle. The signal had been travelling through the void for longer than complex life has existed on Earth. It set out from its source, wherever that was, before our planet had anything more sophisticated than single-celled organisms in its oceans. And it arrived at our telescope during a routine survey, unnoticed, and then sat in a data archive for 6 years before a student scrolling through numbers on a screen finally realised what he was looking at. I want you to imagine that journey for a moment. A pulse of radio energy leaves its source somewhere out in the deep universe, 1.5 billion years ago. The Earth at that time has no animals, no plants, no forests, no oceans full of fish, nothing but microbes. And the pulse begins to cross the dark. It travels for 1 million years, and then 10 million, and then 100 million, threading through the thin gas between galaxies, picking up its dispersion fingerprint as it goes. Continents form and drift on the distant planet it is heading toward. Life crawls out of the water, forests rise and fall, the dinosaurs come and go, human beings appear, learn to make fire, learn to farm, learn to build telescopes, and then, at last, On one ordinary day in 2001, the pulse, after 1.5 billion years in flight, sweeps across 36 metres of dish in an Australian field in less than 5 milliseconds and is recorded as a few lines of numbers and then ignored for 6 years. The patience required of the universe is almost unbearable. The luminosity implied by that distance was staggering. In under 5 milliseconds, this source had released as much energy in radio waves as our sun produces in several days. And I do not mean its entire output across all wavelengths, I mean just in radio. Whatever produced this burst was converting energy into coherent radio emission, with an efficiency and an intensity that had no precedent anywhere in the observational record. The Lorimer burst, as it came to be called, was roughly 10 to 12 orders of magnitude brighter than any known radio pulse at the time. That is a factor of 10 followed by 11 more zeros. It was not a pulsar. It was not one of the rotating radio transients astronomers already knew about. It was not interference from terrestrial electronics. It was something new, something no existing category could hold. And then, for 6 years, almost nothing happened. The astronomical community was deeply skeptical, and with good reason. This was a single event detected by a single telescope, found in archival data years after the fact, with no repeat observation to confirm it. Science does not build theories on lone data points. Worse, in 2010, a researcher named Sarah Burke-Spolaor found other signals in the same park's data that looked, at first glance, similar to the Lorimer burst, but turned out to be interference. The culprit was almost comically mundane: microwave ovens. The staff at the observatory had been opening the doors of microwave ovens before the heating cycle had finished, and the brief flash of escaping radiation was being picked up by the telescope's exquisitely sensitive receivers and recorded in the data as dispersed pulses. These false signals, which were given the name peritons, cast a long shadow over the Lorimer burst. Because if a microwave oven in the break room could produce something that mimicked a cosmic event, how could anyone be sure that the Lorimer burst itself was not some similar artifact, some trick of the equipment or the environment? And I want to pause on the microwave ovens for a moment, because that detail is funnier and more instructive than it first appears. Here was one of the most sensitive scientific instruments ever built, a telescope capable of detecting a whisper of radio energy from across the universe, and it was being fooled, repeatedly, by hungry astronomers opening the breakroom microwave a couple of seconds early to grab their lunch. The escaping burst of microwave radiation, when the door interrupted the cycle, produced a signal that looked, to the telescope, eerily like a dispersed pulse from deep space. It took years of careful detective work to track down the culprit, and the realization, when it came, was almost embarrassing. But it also captures something true about this entire enterprise. We are trying to hear the faintest signals in existence, from the most distant sources imaginable, and to do it we have to filter out everything else, all the noise of our own world, every spark and engine and oven and phone, a deafening roar of human technology, in order to catch the thin, true voices underneath. The peritons were a warning. They said, in effect, be humble, because the universe is subtle, and the things that fool you are often the things closest to home. That humility would prove well placed. The doubt lingered until 2013, when a postgraduate student named Dan Thornton, at the University of Manchester, went looking and found 4 more. 4 new bursts, all in Parkes data, all at high galactic latitudes, far from the plane of the Milky Way where the false signals tended to cluster. All of them with dispersion measures far too large to be explained by the electrons in our own galaxy. The dispersion of some was nearly 3 times greater than the Lorimer burst, implying distances of 5 to 10 billion light-years. With those 4 bursts, the phenomenon was real, and it was extragalactic, and it was not going away. Thornton's team gave it its permanent name: Fast Radio Bursts, FRBs. The name stuck, and the field that would grow up around it over the next decade would become one of the fastest expanding areas of research in all of astrophysics. But naming a thing is not the same as understanding it. and as the next part will show, the closer we looked at fast radio bursts, the stranger, and the more impossible, they became. Part 7. Smaller than a city, louder than a galaxy. As of late 2025, several thousand fast radio bursts have been detected. They arrive from random locations all over the sky. They last between a fraction of a millisecond and a few milliseconds. They occur, by best estimate, at a rate of several thousand per day across the entire sky, every single day. Each one releases in that fleeting instant as much energy as our sun pours out over the course of days. Some of them have been traced back to galaxies billions of light years away. And after nearly 2 decades of intense study, involving hundreds of research teams on every continent, using the most sensitive radio instruments humanity has ever built, we still do not know, with confidence, what causes them. But we're not completely in the dark. The physics of the burst themselves places hard constraints on what the source can possibly be, and those constraints are worth walking through because they back you into a very strange corner. Start with the brevity. The burst is over in about a millisecond. Light travels roughly 300 kilometers in a single millisecond, and that simple fact puts a ceiling on the size of the source. If a burst lasts 1 millisecond, the region producing it must be smaller than roughly 300 kilometers across. Why? Because if the source were larger than that, the light from its far side would arrive measurably later than the light from its near side, and the burst would be smeared out, stretched over a longer duration than we observe. The sharpness of the pulse demands a small emitter. So already we know we're dealing with something tiny by cosmic standards. Then add the coherence. The fact that the burst arrives as a sharp, clean, well-defined pulse, rather than a diffuse wash of static, requires that the entire emitting region fire essentially all at once, in step. This is the difference between a laser and a light bulb. A light bulb throws out photons every which way, out of phase, incoherent. A laser organizes its photons so they march in lockstep, in phase, which is what makes a laser beam so intense and so tight. Fast radio bursts are coherent like the laser. The electrons producing the radiation must be organized, synchronized, emitting together. And ordinary thermal radiation, the kind of light given off by hot gas or a stellar surface, simply cannot produce this. It is too disorganized. Put those two constraints together, and the object producing these bursts must be compact. Extraordinarily compact. Just a few hundred kilometers across or less. In a universe filled with structures spanning millions of light years, like the odd radio circles we started with, the most powerful radio events ever recorded are being produced by something smaller than a mid-sized asteroid. Hold those two facts side by side. A ring 2 million light years wide and a source 300 kilometers wide are both in this same story, and both are at the edge of what we can explain. There is a strange poetry in that pairing, and it is worth sitting with for a moment, because it tells you something about the range of scales the universe operates across. We began this journey with the largest individual structures ever found, rings so vast that the entire Milky Way could rattle around inside them 20 times over. And now, following the same thread of unexplained signals, we have arrived at some of the smallest sources we have ever had to take seriously, objects no bigger than a city, that nonetheless outshine entire galaxies for the duration of a heartbeat. The universe does not respect our sense of proportion. It puts unimaginable power into unimaginably small packages, and it spreads unimaginably faint structures across unimaginably large volumes, and it leaves us to reconcile the two. A fast radio burst is the universe shouting through a pinhole, a single point, smaller than the distance from one city to the next, releasing more energy in 1,000th of a second than our sun manages in days, and doing it so cleanly, so coherently, that the pulse arrives sharp enough to slice through billions of light years of intervening gas and still be recognized for what it is. And then there is the energy, which is the constraint that truly narrows the field. Producing that much coherent radio emission in a single millisecond requires a mechanism that converts energy into radio waves with extraordinary efficiency, and it requires that the emission be coherent, which means the electrons have to be organised and synchronised, emitting in phase, the way a laser does. The numbers involved are genuinely beyond intuition. Astronomers describe the intensity of a source using something called brightness temperature, which is the temperature a normal thermal source would have to reach in order to shine that brightly. For a typical fast radio burst, the brightness temperature exceeds 10 to the 35th power Kelvin. That number has no physical meaning as an actual temperature. Nothing in the universe is that hot. Nothing can be. It is not describing real heat. It is a mathematical flag telling us, unambiguously, that the radiation cannot possibly be thermal. It has to be coherent. Something is organising those electrons with a precision that produces radio emission billions of times more intense than any thermal process could ever achieve. So what kind of object is compact enough, energetic enough, and magnetically violent enough to do all of this? There is exactly one category of known astrophysical object that fits: neutron stars, and more specifically a particular extreme kind of neutron star called a magnetar. A neutron star, you will remember, is the crushed core left behind when a massive star dies, a sphere about 20 kilometers across containing more mass than our Sun. A typical neutron star already has a magnetic field roughly 1 trillion times stronger than the Earth's. But a magnetar is something else again. A magnetar has a magnetic field roughly 1,000 times stronger even than that, 1 quadrillion times stronger than the planet you're standing on. The numbers stop meaning anything, so let me try to give them back some meaning. The Earth's magnetic field, the one that swings a compass needle and shields us from the solar wind, is something you can barely feel. A refrigerator magnet is dozens of times stronger than it. A powerful hospital scanner, the kind that can lurch a steel wrench across a room, is tens of thousands of times stronger than the Earth's field, and a magnetar is 1 quadrillion times stronger than the Earth. If a magnetar were to pass within 100,000 kilometers of you, closer than the Moon, its magnetic field would not merely kill you, it would unmake you. It would distort the very chemistry of your body, because the bonds between atoms, the bonds that hold molecules together, the bonds that make you, depend on the shapes of the electron clouds around atoms, and a magnetar's field is strong enough to crush those electron clouds into thin pencils and rewrite the rules of chemistry itself. You would not be a person anymore. You would not be matter as we understand it. Now let me describe what such a field does even from a safe distance, to the star that carries it. At the surface of a magnetar, the magnetic field is so powerful that it distorts the very shape of atoms, stretching them into thin elongated cylinders aligned with the field lines. It alters the way light itself travels through the space around the star, splitting photons into different polarization states and bending their paths. And it stores titanic amounts of energy in twisted, strained configurations of the field, energy that can be released suddenly and catastrophically in events called starquakes. A starquake is what happens when the rigid crust of the neutron star fractures under the unbearable stress of the magnetic field, and the field lines snap violently into a new configuration, releasing their stored energy in a burst of radiation that can be detected clear across the observable universe. For years, the connection between magnetars and fast radio bursts was theoretical speculation, a strong suspicion without a smoking gun. That changed on the 28th of April in 2020. On that date, 2 telescopes simultaneously detected a burst coming from a magnetar inside our own galaxy. The magnetar carries the designation SGR 1935 plus 2154, and it sits roughly 30,000 light-years away in the constellation Vulpecula. The CHIME telescope in Canada and the STARE 2 array in the United States both recorded a bright radio burst from the magnetar's direction, and it arrived in coincidence with a burst of X-rays detected by orbiting satellites. The radio burst was brief. It was dispersed. It had the spectral characteristics of a fast radio burst, and it came from a known magnetar that had been observed erupting in X-rays and gamma rays for years. It was technically the first fast radio burst ever detected from within the Milky Way, and it established beyond reasonable debate that magnetars can produce fast radio bursts. That should have closed the case, but it did not, and here is the complication that keeps the field from declaring victory. The burst from SGR 1935 plus 2154 was bright by galactic standards, but it was faint by extragalactic standards. It was roughly 1,000 times less energetic than the weakest fast radio burst we detect coming from other galaxies. If that exact same burst had gone off in a galaxy 1 billion light-years away, no existing telescope on Earth would have caught it. It would have been too dim to register. So while magnetars can clearly produce fast radio bursts, the magnetar mechanism as we currently understand it does not obviously scale up to explain the most luminous events in the catalogue, the ones blazing across billions of light-years. Something about the most powerful bursts requires either a more extreme magnetar than any we have ever seen in our own galaxy, or a fundamentally different mechanism altogether, or some environment that amplifies the burst energy in ways we do not yet understand. And then there are the repeaters, which deepen the puzzle from another direction entirely. Most fast radio bursts appear to be one-off events, a single flash from a single location never seen again. But roughly 4% of known fast radio burst sources have been observed to produce multiple bursts, returning again and again. These repeating sources behave differently from the apparent one-offs. Their individual bursts tend to be broader in frequency, more complex in structure, more variable in duration. And some of them are astonishingly prolific. The source designated FRB 2021-02A, the first repeating source ever identified, discovered at the Arecibo Observatory in 2012, has produced thousands of detected bursts across multiple telescopes and frequency bands. It sits in a dwarf galaxy, roughly 3 billion light-years from Earth, embedded in an extreme magnetic environment. Another source, FRB 2022-0912A, discovered by CHIME in 2022, reached observed burst rates of up to 390 bursts per hour during its peak activity. A single source, in a galaxy 400 million light-years away, was screaming so loudly and so frequently that it briefly rivaled the combined output of every other fast radio burst source in the observable sky, all by itself. The existence of repeaters tells us something important, and it is worth slowing down to appreciate why. Imagine you're trying to figure out what caused a single, enormous flash of light that you saw once, years ago, and never again. Your options are wide open. It could have been a one-time catastrophe, an explosion, a collision, something that destroyed itself in the act of shining. There is no way to go back and check, because it never happened again. Now imagine instead that the flash repeats. It comes back, again and again, from the very same point in the sky, sometimes minutes apart, sometimes after weeks of quiet. Suddenly your options narrow dramatically. Whatever it is not destroying itself because it keeps coming back to do it again. It is not a one-time event. It is a process, a recurring engine, a source that survives its own outbursts and reloads and fires once more. That is exactly what the repeating fast radio bursts tell us. Whatever produces these bursts, at least in some cases, survives the event. It is not destroyed. It is not consumed. It bursts, it recovers, and it bursts again, sometimes within milliseconds, sometimes after weeks of silence. The mechanism is not a one-time catastrophe, like a collision or a final explosion. It is a recurring process, driven by a source that persists, that fits comfortably with the magnetar model, where starquakes and magnetic reconnection events can repeat over the long lifetime of the star. But the sheer rate of repetition in the most active sources pushes the energy requirements right to the edge of what magnetar models can comfortably supply. Some analyses have begun to question whether even the total magnetic energy stored in a magnetar's field is enough to power the cumulative radio output we observe from the most prolific repeaters. And then, in January of 2025, a discovery arrived that fractured the emerging consensus even further. the CHIME telescope detected a repeating fast radio burst designated FRB 2024 0209A, and the team traced the burst back to its source. And the source was in the wrong place. It was not in a star-forming galaxy. It was not anywhere near a region of active stellar birth, where massive stars live fast and die young, and leave magnetars behind. It was at the extreme outskirts of a massive ancient elliptical galaxy, a dead galaxy, a galaxy where star formation had ceased billions of years ago. The burst originated roughly 130,000 light-years from the galaxy's centre, in a region where almost no stars exist at all. The most energetic radio events in the universe were coming from the emptiest, quietest neighbourhood, in one of the oldest, most lifeless galaxies ever associated with a fast radio burst. This should not happen under the Standard Model. If fast radio bursts come from magnetars, and magnetars form when massive stars explode as supernovae, then fast radio bursts should be found in galaxies where massive stars are being born and dying. Young galaxies, active galaxies, star-forming galaxies, not 11-billion-year-old elliptical galaxies, where the last supernova went off billions of years before the burst we detected even left its source. The researchers proposed that the source might live in a globular cluster, a dense spherical swarm of ancient stars where exotic interactions between compact remnants, white dwarfs collapsing, neutron stars merging, could forge a magnetar through a delayed roundabout formation pathway, rather than the direct route of a single massive star exploding. If that is confirmed, it would mean the universe has more than one way to build the engines behind fast radio bursts. It would mean the phenomenon is not tied to a single origin story. It would mean the cosmic scream can come from sources as different as the youngest stellar nurseries and the oldest stellar graveyards. And we are, after thousands of detections, still finding out how many different ways the universe has to surprise us with the same kind of signal. Part 8. The Scream that Weighed the Universe. There is a number that captures the scale of what we're dealing with, and it is worth saying plainly. Several thousand fast radio bursts go off across the sky every single day. Most of them we never see, because no telescope happens to be pointed at the right patch of sky at the right millisecond to catch them. We catch only a tiny fraction of what is actually happening, and the ones we do catch arrive from galaxies spread across the entire observable universe, out to distances of 8 billion light-years, and possibly beyond. Every one of them is a flash from a source we cannot fully explain. But here is the turn in this part of the story, the part that takes something baffling and makes it useful, almost miraculously so. Because each one of these bursts carries information, not only about its mysterious source, but about everything it passed through on its way to us. Remember dispersion, the effect that smears a burst's frequencies, because free electrons in space slow the lower frequencies more than the higher ones. The amount of dispersion in a fast radio burst is a direct measurement of the total number of free electrons lying between the source and our detector, all along the line of sight. This means that every fast radio burst is, in effect, a probe, a cosmic ruler, a measuring stick that stretches from its home galaxy all the way to ours, counting every free electron in between as it passes. The very thing that makes these bursts mysterious, the way they smear as they travel, also turns them into instruments for weighing the universe. And in 2020, a team led by the astronomer Jean-Pierre Macquart used a sample of fast radio bursts whose home galaxies had been precisely located to do exactly that. By measuring the dispersion of bursts at known distances, the team effectively weighed the gas spread thinly between the galaxies, and what they found resolved a problem that had haunted cosmology for 2 decades. They found the missing baryons. Let me explain what that means, because it is one of the quiet triumphs of modern astronomy. Baryons are ordinary matter, the normal stuff that makes up stars and planets and gas and you and me, as opposed to the mysterious dark matter and dark energy that dominate the universe's budget. For decades, astronomers had a frustrating accounting problem. When they added up all the ordinary matter they could directly observe, All the matter in stars, in galaxies, in the hot gas of galaxy clusters, the total came to only about half of what the standard cosmological model said should exist. The other half was simply missing. Not dark matter, which is a separate thing entirely, but ordinary matter, the kind we know how to detect and yet could not find. It was out there somewhere, the theory insisted, but it was too diffuse and too cool to show up in any telescope. For 20 years, half of the normal matter in the universe was unaccounted for. Fast radio bursts found it. The missing matter was in the intergalactic medium, spread impossibly thin through the vast empty volumes between the galaxies, far too sparse to emit or absorb enough radiation to be seen by any conventional means, but just dense enough to leave its fingerprint on the dispersion of radio bursts passing through it. When McQuart's team measured how much the burst had been smeared, they were counting that hidden gas, and the total they arrived at matched the predictions of Big Bang nucleosynthesis and the cosmic microwave background almost exactly. The accounting finally balanced. A phenomenon we do not understand, produced by sources we cannot identify, travelling through a medium we could not previously measure, solved a problem that had persisted for 2 decades. The scream told us what the silence could not. I find that genuinely beautiful, and I want to dwell on it, because it cuts against the grain of how we usually think about mysteries. We tend to assume that an unsolved problem is useless until it is solved, that a question mark is just a gap waiting to be filled. But here, the unsolved thing, the fast radio burst whose origin still eludes us, became the tool that solved a completely different unsolved thing. The mystery was the instrument. We did not have to understand what made the bursts in order to use the burst to weigh the universe. And that is worth remembering as this story builds, because it suggests that the value of these strange signals is not only in the answers they eventually give up, but in what they let us measure along the way, while they are still mysteries. There is a deeper point hiding in here too, about how knowledge actually grows. We like to imagine science as a tidy march, one mystery solved, then the next, each one closed before the following one is opened. But that is not how it really works. In practice, the unsolved problems pile up alongside one another, and sometimes they turn out to be connected in ways nobody anticipated, so that progress on one quietly delivers progress on another. The missing baryons were a problem in cosmology, the study of the universe on its larger scales. Fast radio bursts were a problem in transient astronomy, the study of brief flashing events. The two communities barely overlapped. They published in different journals, attended different meetings, thought in different terms, and yet the answer to one was carried, encoded, inside the unsolved data of the other, waiting for someone to realize that the smear on a mysterious burst was a census of invisible gas. Nobody planned that. Nobody could have. It emerged because the universe is more interconnected than our neat divisions of it suggest, and because a few people were willing to look at a strange signal and ask not only what is it, but what has it touched on its way to me? That question, what does this signal pass through, is going to matter enormously by the time we reach the end of tonight's journey, and still, the bursts keep coming. CHIME, the Canadian Hydrogen Intensity Mapping Experiment, detects 2 to 3 fast radio bursts every day, and it is currently undergoing upgrades that will let it pinpoint burst locations with unprecedented precision. CHIME is a strange and wonderful instrument, by the way. It does not look like a telescope at all. It has no dish that swivels to track a target. It is a set of 4 enormous half pipes, like the ramps a skateboarder might use, lying motionless on the ground in a valley in British Columbia, staring straight up. It cannot point. It simply waits, watching the strip of sky that passes overhead as the Earth turns and lets the universe rotate its targets into view. And because it never has to move, because it watches such a wide swathe of sky at once, it catches fast radio bursts at a rate that the great steerable dishes never could. It is a reminder that sometimes the way to see more is not to build a bigger eye, but to build a stiller, wider, more patient one. The square-kilometre array, an enormous radio observatory being built across sites in both Australia and South Africa, is being designed with the explicit ability to detect and localize fast radio bursts at rates and sensitivities far beyond anything we can do today. When it comes fully online, it is expected to find these bursts not by the handful, but in floods, possibly capturing in a single day what took years to accumulate before. And every one of those bursts will be another ruler laid across the cosmos, another whisper from a source we cannot name, another smear of dispersion encoding the weight of the gas between here and there. Every new telescope that opens its ears to the radio sky finds more of them. Every new survey turns up sources that push at the boundaries of what our models can explain. The catalogue grows, the patterns emerge, and the exceptions, the bursts that do not fit, multiply just as fast as the confirmations. Something is producing the most powerful coherent radio events in the observable universe, from regions smaller than a city, scattered across billions of light years, in flashes so brief they are over before the light from the start of the burst has crossed the width of a large island. Some sources do it once and never again. Some do it hundreds of times an hour. And the question of what they truly are remains, after all of this, fundamentally open. And notice the shape of the journey we have just taken through these bursts, because it is the shape of the whole story in miniature. We began with a single flash, found by accident, doubted for years, nearly dismissed as the work of a microwave oven. We watched it multiply into a category, then a flood, then a daily occurrence across the entire sky. We narrowed the source down to something smaller than a city, and more violent than almost anything in nature. We linked it tentatively to magnetas, and then immediately found bursts that the magnetar story could not quite hold. Bursts from dead galaxies, bursts too frequent and too powerful for the models to comfortably feed. And along the way, almost as a side effect, the mystery handed us the missing half of the universe's ordinary matter. Every answer opened two new questions. Every confirmation came stapled to an exception. That is not the rhythm of a field that is closing in on a complete picture. It is the rhythm of a field that has just realized how much larger the picture is than it thought. And if it were only the fast radio bursts, you might call it a single hard problem and leave it there. But fast radio bursts are not the only signals straining our models. There are at least two more anomalies sitting in our data right now, and one of them is hiding in the oldest light that exists. Part 9. The cold spot and the impossible pulsar. I want to introduce two more signals now, more quickly than the others, because their job in this story is not to be solved in front of you. Their job is to show you that the pattern we have been tracing does not stop with circles and pulses and bursts. It keeps going. It reaches into the oldest light in the universe, and it reaches into the behavior of objects we thought we understood completely. Start with the oldest light. In the constellation Eridanus, in the southern sky, there is a patch of the cosmic microwave background that is colder than it should be. Now, the cosmic microwave background is the faint afterglow of the Big Bang, the radiation left over from when the universe was only 380,000 years old, and it fills the entire sky in every direction. It is the most precisely measured radiation field in the history of physics. Its temperature is staggeringly uniform, the same across the whole sky to a precision of roughly 1 part in 100,000. The tiny variations that do exist, the slightly hotter and slightly colder spots, encode the density ripples of the infant universe, and they follow a specific statistical pattern that the standard cosmological model predicts. The cold spot does not fit that pattern. It spans roughly 5 degrees of sky, more than 10 times the apparent width of the full moon, and it is about 70 millionths of a degree colder than the average temperature of the background, which itself sits only about 2.725 degrees above absolute zero. 70 millionths of a degree sounds like nothing, but against a field that uniform measured that precisely, it is a glaring anomaly. It is too large, too cold, and too statistically improbable to be comfortably dismissed as a random fluctuation. The odds of finding a deviation this extreme by chance in the kind of field the standard model predicts have been estimated at less than 2%. Now, if you are a long-time listener, you have met this cold spot before, on a previous journey through the cosmic web and the great voids, and so I will not belabor it. But it belongs here, in this catalogue, because it is the same kind of thing we keep finding. A signal in our best data that our best models did not predict. The leading conventional explanation is a supervoid, an enormous underdense region in the large-scale structure of the universe, lying along our line of sight to the cold spot. As the background photons cross that vast emptiness, they lose a tiny amount of energy to the accelerating expansion of space, an effect with the name the integrated Sachs-Wolf effect. And the Dark Energy Survey has confirmed that such a void does exist in that direction, roughly 1 billion light-years across, one of the largest underdense regions ever identified. But careful calculation shows that the supervoid alone cannot account for the full temperature deficit. It explains some of the coldness, not all of it. The gap remains. More recent studies published in 2023 and 2024 have raised an alternative and a slightly unsettling one. They found a statistically significant correlation between the positions of nearby spiral galaxies and cold spots in the background, which suggests the existence of a previously unrecognized foreground component, a systematic temperature decrement around local galaxies that could be imprinting patterns on the background that we have been reading as primordial. If that effect is real, it would mean that part of what we have been interpreting as a signal from the birth of the universe is actually a signal from much closer to home, from much more recent structures, contaminating the ancient light. We may have been misreading the message, mistaking the foreground for the background, confusing a nearby whisper for a primordial shout. And notice that this is the same lesson as Jaminga at the wrong frequency, just turned inside out. There, we missed a real signal because we were not tuned to it. Here, we may be reading a signal that is not the one we think it is. Either way, the limitation is in us, in our instruments and our interpretation, not in the universe. There is a quiet vertigo in that idea if you let it land. The cosmic microwave background is the closest thing we have to a baby photograph of the universe. It is the light that was set free when the cosmos cooled enough, 380,000 years after the Big Bang, for atoms to form and for light to travel freely for the first time. Every map of it, every measurement, is in a real sense a portrait of the universe in its infancy, and we have treated it as sacred, as the cleanest message we will ever receive from the dawn of everything. And now, there is a suggestion, only a suggestion so far, that some of what we have been reading in that baby photograph is not the baby at all. That nearby galaxies, structures that formed billions of years later, may be leaving their own faint thumbprints on the image, and that we have been mistaking those thumbprints for features of the original. If that is true, it does not mean the photograph is worthless. It means we have to learn to tell the smudges on the lens apart from the face in the picture. And that is humbling, because the cosmic microwave background is the field we were most confident we understood. If even there, in our most precise measurement, our perception may be subtly fooling us, then the lesson of this whole story reaches all the way back to the beginning of time, and then there is the signal that should not exist at all. In 2023, the Murchison Wide Field Array in Western Australia detected an object designated GPMJ 1839-10, and it emits radio pulses every 21 minutes and 58 seconds. The pulses last anywhere from 30 seconds to 5 minutes, and here is the remarkable part. When astronomers went back into the archives, they found this signal present in data stretching all the way back to 1988. 35 years of consistent periodic radio emission from a source roughly 15,000 light-years away in the constellation Scutum. The problem is not that the signal exists. The problem is that, according to our physics, it should not. If the source is a neutron star, as the polarization properties of its signal strongly suggest, then its rotation period places it far below something astronomers call the death line. The death line is a boundary in the physics of neutron stars. Below it, a neutron star's particular combination of magnetic field strength and rotation rate is simply not enough to power the cascades of particle production that generate coherent radio emission. A neutron star rotating once every 22 minutes should be, by every model we have, radio silent. Its magnetic field should be far too weak, relative to its slow rotation, to accelerate particles to the energies required to make radio waves. And yet GPMJ 1839-10 has been broadcasting steadily for at least 35 years, its rotation period unchanged to within fractions of a millisecond across that entire span. How? Nobody is sure. A magnetar starquake could temporarily reignite radio emission from a dead pulsar, but starquakes dissipate within years, not decades. A highly magnetized white dwarf could in principle rotate this slowly, but no known white dwarf produces radio emission at this luminosity. A binary system involving a white dwarf and a companion star was proposed in early 2026, with the pulsing arising not from the object's rotation, but from its magnetic axis periodically sweeping through the stellar wind of its companion. The community remains divided. No single explanation accounts for all of the observed properties at once, and so the signal continues, every 22 minutes, from a source that our best models insist should be silent. Each of these phenomena on its own is a manageable puzzle, a curiosity in the margin of an otherwise coherent textbook. The cold spot is an oddity in cosmology. The impossible pulsar is a challenge to neutron star physics. The odd radio circles are a mystery in extragalactic radio astronomy. Geminga's halo is a problem in high-energy astrophysics. Fast radio bursts are an open question in transient astronomy. Individually, each one is a single loose thread in an otherwise intact fabric. But in the next part, I want to do something we almost never do. I want to stop looking at the threads one at a time and step back far enough to count them all together and notice which direction they are pulling. Part 10. The pattern. Nobody named. There is a habit in science that serves the discipline beautifully under normal circumstances and fails it badly at moments of genuine revolution. The habit is specialization. The radio astronomer who discovered the odd radio circles does not attend the same conferences as the particle physicist, analyzing positron data from the space station. The team studying Geminga's gamma-ray halo does not share a hallway with the team cataloguing fast radio bursts. The researchers modelling the cold spot in the cosmic microwave background do not typically read the papers about synchrotron emission from intergalactic shock waves. Each discovery lives inside its own literature, its own funding stream, its own community of experts who speak their own dialect of the science. Each signal gets studied in isolation, and the pattern that might connect them, if anyone were to step far enough back to see it, has no name, because no single discipline owns it. It falls in the gaps between the specialties, where no one is quite responsible for looking. So let us step back now. Let us look at everything we have examined, not at the details, but at the shape of it. In 2019, a new generation of radio telescope, with unprecedented sensitivity to faint diffuse structures, revealed enormous rings of synchrotron radiation hanging in deep space, structures up to 2 million light-years across, invisible at every wavelength except radio, produced by mechanisms that 3 competing hypotheses still cannot decide between. And the crucial thing is this: the odd radio circles had been there for billions of years. We found them only when our instruments became capable of detecting them. Before ASCAIA and its phased array feeds, the circles did not exist in our catalogue of the universe. After ASCAP, they did. The universe did not change. Our ability to perceive it did. 800 light-years away, a dead star the size of a city has been showering our planet with antimatter for 300,000 years. Geminga was invisible to radio telescopes because it broadcast below the band anyone thought to search. It was invisible to optical telescopes because it gives off almost no visible light. Its gamma-ray halo, large enough to dominate the night sky if our eyes could see gamma rays, went undetected until 2017 because no instrument with the right sensitivity had ever been pointed at it for long enough. The positron excess that it helps explain was not even measurable, until we bolted a particle detector to the outside of a space station. The antimatter was always arriving. The gamma rays were always there. We simply had no way to know. And from every direction in the sky, thousands of times a day, bursts of radio energy lasting less than the blink of an eye arrive from sources scattered across the observable universe, each carrying the energy output of days of sunlight compressed into a single millisecond. We have detected thousands of them. We have traced roughly 100 to their home galaxies. We have identified a single source within our own galaxy and linked it to a magnetar. And after nearly 2 decades of work, the fundamental question of what produces the majority of these bursts remains unanswered, and every new discovery narrows the possibilities while introducing fresh exceptions. The bursts from dead galaxies, the repeaters whose appetite for energy strains the magnetar models, the sources that fire once and vanish forever. Each exception is a data point. Each data point is a signal, and the signals are accumulating faster than the theories. Now here is the thing I most want you to see, the thing that is hiding in plain sight in all of this. Every one of these signals was discovered, not because we went looking for it, but because a new instrument, operating at a sensitivity or a wavelength or an energy range that no previous instrument could reach, revealed something that was already there. Not something new, something old, something that had been broadcasting, radiating, pulsing or glowing for thousands or millions or billions of years before we ever developed the capacity to detect it. The universe did not suddenly start producing odd radio circles in 2019. It did not begin generating fast radio bursts in 2007. Geminga did not start emitting positrons when we switched on the spectrometer. The cold spot did not appear when our satellites began mapping the background. These signals predate not only our instruments, but in many cases our entire species. They have been part of the fabric of the cosmos for longer than complex life has existed on Earth, and we found them only in the last handful of years, some of them in the last handful of months. This is the pattern that nobody named, and the pattern is not in the signals themselves, it is in the timing, in the sequence, in the accelerating rate at which our instruments are revealing phenomena that existing models did not predict and cannot yet fully explain. Now, you might say, of course new telescopes find new things. That is just how science works. Every generation of instruments sees what the previous generation could not, and that is true. That is the normal progression of observational science, and by itself it would not be remarkable. But there is something about the present moment that is not normal, and it is not the discovery of new things. It is the ratio. The fraction of new discoveries that fall outside our existing theoretical frameworks is not shrinking as our models improve. It is growing. We are not converging on a complete picture of the universe. By this measure, we are diverging from one. Every new instrument opens a window onto a sky that is more complex, more active, and more saturated with unexplained signals than the model suggested it should be. Think about the history for a moment. In the 1950s and 60s, radio astronomy revealed quasars, pulsars, and the cosmic microwave background. Each one required new physics. Each one was eventually absorbed into the standard model, expanding it, deepening it, making it more complete. The quasars turned out to be the blazing cores of distant galaxies, powered by supermassive black holes. The pulsars turned out to be spinning neutron stars, the same kind of object we have been following tonight. The cosmic microwave background turned out to be the afterglow of the Big Bang itself, the discovery that more than anything else confirmed how the universe began. Each of these was, at the moment of discovery, a complete shock, a thing that fit nowhere, and each was, within a decade or two, understood, named, and folded into the textbook. In the 1990s and 2000s, X-ray and gamma-ray observatories revealed magnetars, gamma-ray bursts, and the accelerating expansion of the universe. Again, new physics was required. The gamma-ray bursts for years were among the deepest mysteries in astronomy, brief flashes of the most energetic light in existence, arriving from random directions, and it took decades to establish that they mark the deaths of massive stars and the mergers of neutron stars. The accelerating expansion forced us to invent dark energy, a mysterious something that makes up most of the universe and that we still do not understand. Again, the models stretched to accommodate it. But in each of those earlier eras, the number of genuinely unexplained phenomena at any given moment was small, a handful, manageable. The questions got answered, one by one, within years or decades. The mystery would arrive, the community would converge on it, and eventually it would yield. That was the rhythm. Surprise, struggle, understanding, repeat. Now look at where we actually stand. The odd radio circles discovered in 2019 still unexplained. Fast radio bursts discovered in 2007, their source mechanism still debated after nearly 2 decades. The cold spot, identified in 2004, still anomalous after 20 years of analysis. Long-period radio transients below the death line, discovered in 2022 and 2023, still defying theoretical explanation. Jaminga's full positron contribution, measured only in 2019, still reshaping our understanding of cosmic ray physics. The catalogue is not closing, it is opening, and the next generation of instruments is already on the way. So before we talk about what they might find, we have to ask a harder question, the one this whole pattern has been circling toward. If the universe has been this loud, this whole time, and we have only just begun to hear it, then what does that do to the oldest question we have ever asked about the sky? Part 11. Are we alone, or were we deaf? Think about what this means for the question we carry with us every time we look up at a clear night sky. The question that sits underneath every signal in this story, every anomaly, every unexplained burst and ring and halo. Are we alone? The question, as it is usually framed, comes with a hidden assumption baked into it. The assumption is that if intelligent life existed elsewhere in the universe, we would have detected its signals by now. That is the foundation of the famous Fermi paradox. If they are out there, the reasoning goes, then where are they? The logic seems airtight. We have been listening for decades. We have built increasingly sensitive instruments. We have scanned millions of star systems for narrow band signals, the kind of focused, artificial transmission a technological civilization might produce, and we have found nothing confirmed. So the argument concludes, perhaps there is nothing to find. Perhaps the silence is real, and we are alone. But look at what else we failed to detect during those very same decades. We failed to detect odd radio circles, structures millions of light years across, until 2019. We failed to detect the full extent of Jaminga's positron halo until 2019. We failed to detect fast radio bursts until 2007, even though they go off thousands of times a day at energies that exceed the daily output of our sun. We failed to detect long-period radio transients below the death line until 2022. We failed to detect gravitational waves until 2015, despite the fact that merging black holes have been warping space-time with them for billions of years. In every single one of these cases, the signal was there. The signal had always been there. We were simply not listening at the right frequency, or with the right sensitivity, or at the right time, or with the right instrument. So here is the question that follows, and it is a heavy one. If we missed the loudest natural signals in the universe for decades, because our instruments were not tuned correctly, what confidence can we really place in the claim that the absence of detected artificial signals means the absence of artificial signal sources? And the honest answer is, very little. We have been listening for extraterrestrial intelligence with instruments that, until very recently, could not even detect the natural phenomena unfolding in our own galactic neighbourhood. We were searching for whispers while standing inside a thunderstorm we could not hear. Let that image sit for a moment, because I think it is the truest thing in this entire story. We were searching for whispers while standing inside a thunderstorm we could not hear. For decades, dedicated scientists pointed their instruments at the stars and listened for the faint, deliberate signal of another mind, and heard nothing, and slowly the silence began to feel like an answer. The Great Silence, people called it. And it weighed on us. It suggested we might be alone in a way that is almost too large to feel, alone in a galaxy of 400 billion stars, alone in a universe of 2 trillion galaxies. But what we have learned, signal by signal, ring by ring, burst by burst, is that during the very decades we spent calling the universe silent, it was in fact roaring. Roaring in radio circles the size of galaxies. Roaring in millisecond screams thousands of times a day. Roaring in antimatter and gamma rays and gravitational waves that pass through our bodies unfelt. The silence we heard was never the universe holding its breath. It was the limit of our own hearing. And once you understand that, the great silence stops sounding like a verdict and starts sounding like a description of where we happen to be standing and how little of the storm we'd yet learned to detect. I want to be careful and precise here, because this is easy to misunderstand. This is not an argument that extraterrestrial intelligence exists. I am not telling you the aliens are out there. It is an argument that we are not yet in a position to meaningfully claim that they are not. There is a principle that gets repeated in science, that absence of evidence is not evidence of absence, and it is often overused, trotted out to defend all kinds of wishful thinking. But here it applies with real force. The absence of evidence, in a search conducted with instruments that we now know were blind to entire categories of natural astrophysical phenomena happening right next door, is not evidence of absence. It is evidence of the limitations of the search. It tells us about our instruments, not about the universe. And those limitations are not safely behind us. They are still with us right now. The instruments coming online in the next decade will be more sensitive than anything we have today, by factors of 10, of 100, of 1,000. The Square Kilometre Array, the next generation of cosmic microwave background experiments, new gravitational wave detectors, the Vera Rubin Observatory, with its enormous camera scanning the entire visible sky every few nights. If the pattern of the last 2 decades holds, and there is no reason to think it will suddenly stop, then these instruments will reveal phenomena we have not predicted, signals we are not expecting, structures we did not know were there. And somewhere in that flood of new data, from a universe we are only beginning to perceive in its full complexity, there may be something that is not natural, something that carries the unmistakable signature of intention, something that, when we finally develop the right instrument, tuned to the right frequency, pointed at the right patch of sky at the right millisecond, will be impossible to mistake for anything else. Or there may not be. I have to say that too because intellectual honesty demands it. The universe may turn out to be exactly as empty of intelligent signal as it currently appears. The silence may be real after all. We may be the first, or the only, or the last. That possibility is every bit as real as any other, and nothing in this story rules it out. But the honest assessment of where we actually stand is not that we have searched thoroughly and found nothing. It is that we have barely begun to search, with instruments that have repeatedly proven inadequate to detect even the most energetic natural phenomena in our own immediate cosmic environment. And we have been drawing sweeping conclusions from that inadequate search about the existence or non-existence of signals we have not even defined, from sources we cannot predict, at frequencies we may not yet have the technology to detect. Humility is not a common posture in science, and I say that with affection for the enterprise, not contempt. Science runs on confidence, on the conviction that the models are close enough, the data is sufficient, the framework is sound, and that confidence has earned extraordinary results. It put human beings on the moon. It predicted the Higgs boson before anyone ever saw one. It captured the shadow of a black hole on a photograph. Confidence works. But confidence, applied to questions we're not yet equipped to answer, becomes something else. It becomes premature closure. It becomes the quiet assumption that because we have looked and not found, there is nothing there to find. And the history we have traced tonight, the history of signals that were always there but required new eyes to see, should give us pause before we close any question permanently, especially the largest one. because if we were this deaf to the natural universe shouting all around us, we should be very slow to declare, with confidence, that no one else is out there. The silence we heard may never have been the universe's. It may have been ours. And that single shift from are we alone to were we simply deaf changes the meaning of every quiet night sky you have ever stood beneath. Part 12. Newborn Eyes. There is a moment in the development of every sensory organ, in every creature that has ever evolved the ability to perceive its surroundings, when the organ begins to function, but the mind behind it has not yet learned to make sense of what it is receiving. A newborn human opens its eyes for the very first time and sees light. Not shapes, not depth, not faces, just light. A wash of undifferentiated brightness flooding into a visual cortex that has no framework yet for organizing any of it. The hardware is online, the software is not. Interpretation comes later, pattern recognition comes later, understanding comes later. First, there is only the raw, overwhelming, unprocessed flood of signal, pouring in faster than the mind can sort it. That is where we are. That is exactly where we are. We built the eyes, we pointed them at the sky, and what came flooding in was not the orderly, well-behaved cosmos we had prepared ourselves to see. It was a wall of signal, radio circles the size of galaxy clusters, antimatter raining down from invisible dead stars, millisecond screams carrying the energy of suns from billions of light-years away, cold spots in the oldest light in existence that do not match the models, pulsing sources that defy the very boundaries we drew to define what should and should not be possible. All of it arriving at once, all of it layered on top of itself, all of it demanding interpretation from a species that built its first radio telescope less than a single century ago. 1 century. That is the entire span of time during which human beings have been able to hear the universe in radio at all. Before Carl Jansky's rotating antenna detected radio emissions coming from the Milky Way in 1932, the radio sky did not exist for us. It was there. It had been there for 13.8 billion years. Every pulsar that has ever spun, every magnetar that has ever erupted, every fast radio burst that has ever fired, every synchrotron electron that has ever spiraled through a magnetic field, all of it was broadcasting. The universe was saturated with radio signal from the moment the first stars ignited and the first magnetic fields curled into being. And for the entire span of human history up to 1932, every philosopher, every astronomer, every person who ever looked up and wondered, we heard none of it. We lived inside a symphony, and we perceived silence. And consider how that first radio discovery even came about, because it follows the pattern exactly. Carl Jansky was not an astronomer hunting for the secrets of the galaxy. He was an engineer, working for a telephone company, given the thoroughly practical task of figuring out what was causing the static that interfered with transatlantic radio telephone calls. He built a rotating antenna, a contraption his colleagues nicknamed Jansky's merry-go-round, and he set about cataloguing the sources of hiss and crackle. He found the static from nearby thunderstorms, and the static from distant thunderstorms, and then he found a third source, a faint steady hiss that rose and fell once a day, and at first he thought it must be the sun. But it was not quite keeping time with the sun. It was keeping time with the stars. And eventually he realized that the hiss was coming from the center of the Milky Way, from the constellation Sagittarius, from the heart of our own galaxy. A telephone engineer, looking for the cause of dropped calls, had accidentally become the first human being to hear the universe in radio. He did not set out to open a new window on the cosmos. He stumbled through it while doing his job, and that too is part of the pattern. The universe is so full of signal that even when we are not looking for it, it finds its way into our instruments and waits for someone curious enough to ask where the hiss is coming from. Now multiply that by every wavelength we have learned to detect since. X-rays, opened up as an astronomical tool in the 1960s. Gamma rays, mapped from orbit beginning in the 1970s. Gravitational waves, first detected in 2015. Neutrinos from astrophysical sources, confirmed in 2017. Each new channel we opened released a flood of information that had been propagating through the cosmos for billions of years, passing through our planet, through our homes, through our bodies, completely unnoticed. The gravitational wave from two merging black holes, a billion light-years away, stretched and compressed every atom in your body by a fraction of the width of a proton as it passed through you. And you felt nothing. The neutrinos from a distant supernova passed through the Earth at nearly the speed of light, trillions of them threading through every square centimetre of the planet's surface every second, and not one of them disturbs a single atom on its way through. The gamma rays from Geminga's halo have been arriving at the top of our atmosphere for 300,000 years, and the first human being to know they existed was born in the 20th century. We are not observers who arrived late to a quiet universe. We are listeners who are deaf and have only just begun to hear, and the universe we're hearing is not quiet. It never was. The quietness was in us. So where does that leave us? On this small rocky planet orbiting an ordinary star in the suburbs of an ordinary barred spiral galaxy. We have spent the last 93 years building ears, imperfect ears, narrow ears, ears that can hear maybe one octave of a symphony that spans the entire electromagnetic spectrum and beyond. Ears that miss most of what is being said, because they are tuned to the wrong band, or aimed at the wrong patch of sky, or not sensitive enough to catch the faintest signals, or not fast enough to catch the briefest ones. We are listening to the universe through a keyhole, and what we have heard through that keyhole in just the last few years has already overthrown our expectations, filled our journals with anomalies, and revealed that the sky we thought we knew is a pale sketch of the sky that actually exists. So I cannot help but wonder, what will we hear when we finally open the door? I think about the people who will build that door. They are alive right now, some of them. The astronomer who will identify the next entirely new class of object is, this very moment, perhaps a student, perhaps a child looking up at the night sky for the first time and feeling that small pull of wonder that draws a person toward this work. The instrument that will reveal whatever comes after fast radio bursts is being sketched on whiteboards, argued over in funding committees, slowly taking shape in the minds of engineers who do not yet know what they will find with it. That is how it has always gone. Karl Jansky did not know he was opening the radio sky. Anna Kapinska did not sit down at her desk that morning expecting to name a new kind of cosmic structure. David Narkovich was a student doing an assignment when he found the loudest radio flash anyone had ever seen. The great discoveries do not announce themselves. They arrive quietly, in the form of something that does not fit, noticed by someone who happened to be paying attention. And there is something deeply hopeful in that, when you think about it. It means the next revolution in our understanding of the cosmos is not locked away behind some impossible barrier. It is waiting in the data, waiting in the sky, waiting for the right eyes and the right instrument and the right moment of honest attention. It has been waiting in many cases for billions of years. It can wait a little longer, but not, I suspect, very much longer. Because we are building the doors faster than ever, and the universe, as we have seen, has never been short of things to show us once we learn how to look. Anna Kapinska wrote 2 letters and a question mark on an image of something no human had ever seen before. WTF. And I told you we would come back to it. Because that moment, that honest, unguarded, unscientific response to something genuinely new, captures something essential about where we stand. We're not at the end of discovery. We're not at the point where the catalogue is nearly complete and only a few loose ends remain to be tidied up. We're at the beginning. At the moment when our instruments have become just barely powerful enough to reveal that the sky we thought we knew is a faint pencil sketch of the sky that is really out there. In the language of science, those 2 letters and a question mark are not an expression of confusion. They are the beginning of understanding. Because the most important discoveries in the history of astronomy have never begun with an answer. They have begun with the honest recognition that something is there that should not be, and the willingness to keep looking at it until it gives up what it is. Every signal in this story is a reminder that the universe does not wait for us to be ready. It broadcasts whether we are listening or not. It produces phenomena at every scale and every energy, whether or not we have the instruments to detect them. It does not simplify itself to match our models. It does not limit its complexity to whatever our current generation of telescopes can resolve. The signals are not stopping. They are not slowing. They are not becoming more predictable as our instruments improve. They are doing the opposite. They are revealing a cosmos that is wilder, noisier, more layered, and more deeply strange than any generation of astronomers before us has ever encountered. The rings are in the radio sky. The antimatter is in the particle data. The screams are in the millisecond bursts. The anomalies are in the oldest light that exists. The impossible pulsars are below the death line. And the explanations, the theories, the frameworks that will eventually make sense of all of it have not been written yet. Somewhere, right now, tonight, a telescope is recording data that contains a signal no one has noticed. It is sitting in an archive, on a server, in a file that a student has not yet opened. It may be a ring. It may be a burst. It may be a periodicity that no model predicts. It may be something we do not even have a name for, and it will be found the way all the others were found. Not by an algorithm, not by a theory, by a pair of human eyes, scrolling through data, noticing something that does not fit, and having the courage to label it honestly. The universe is speaking. It has always been speaking, and the only question that really matters now is whether we are willing to keep building better ears, to keep opening new windows, to keep listening at frequencies we have not yet tried, and to keep admitting, every single time we find something we cannot explain, that the two most honest letters in all of science are the ones a radio astronomer wrote on an image in 2019, when the universe handed her something it had been holding out toward us for billions of years, waiting for the moment we would finally be able to see it, and then to keep listening.